This is a longer worked example for analysis of variance. So the problem is shown on the screen. In an experiment, 4 groups of chemicals are going to be tested, and we have 15 vials in each group. We're told the common standard deviation is 3, and the total sum of squares is 1500. Remember, sum of squares represents a measure of variance. We want to know, is there evidence of a difference between the groups? To judge this, we'll use a critical value of f at 3.5. So to do this, we need to start out by filling in the table. Now let's take a look at the table for analysis of variance. We have sum of squares, which provides a way to keep track of the variability between either groups or the treatments. We're using treatments in this case, and the observations, which are commonly called errors or sometimes within groups. Now, if you recall from the problem, go back here for a moment, that the total sum of squares is 1500. So we'll put that in our table here. Now let's go back and take a look at the previous. What else do we know? We got 4 groups of chemicals. So this is going to provide us the degrees of freedom for treatments, which, as you recall, is K minus 1. So what do we have? We have 4 minus 1, which is 3, obviously. So that's going to go here. Now, each group has 15 vials, so 4 times 15 gives us 60 total observations. So the sum of the squares for the errors, which is where we're going to use this value next, is big N, which is this value, minus K, which is this value. So we end up with 56. Let's put that in our table. So this adds up to 59, and this is just a bookkeeping cell where n minus 1 provides a way to keep track of the degrees of freedom. There's some more information still to pull out of this. Let's go take a look at that. The common standard deviation is 3. Now, recall this cell here is the common variance. So if standard deviation is equal to 3, then the variance is equal to 3 squared, or 9. So that goes here. So this is all the information we're given, other than the critical value of f. And we'll put that in over here just to be complete. Now, whenever you've got 2 of the 3 numbers in a row or a column, you can always get the third. For instance, to find out what goes into the sum of the squares of the errors cell, we simply go 56 times 9. So this is 504, I believe. Let's see what this is. This is 4, and that's 54. 9 times 6 is 54. 9 times 5, this is 504. So that goes here. So whatever value is here, added to this, gives us 1500. So this should be 996. Make that a better 9. We'll fix that up. That's not very good. One more undo. There we go. 996. Now, to get mean squares, we take 996 and divide by 3. So that should be 332. The test statistic f is going to be 332 divided by 9. In other words, this cell divided by this cell. And that's just a quick calculator computation. We'll do that right now. We know it's going to be around 30 because 332 divided by 9 is almost 332 divided by 10, right? 332 divided by 9 gives us 36.8. Well, 36.9. And this is substantially larger than this, so we have evidence to reject the null hypothesis. The null hypothesis, of course, is that all the mean values from our experiments are the same. Well, that's certainly not true according to this evidence. This suggests at least one of them is different. If I want to report the test statistic under the null hypothesis, I'll write F is equal to 36.9 on 3 and 56 degrees of freedom. And there we go. And that concludes this example.